Hi, Nick.
Hey Pete,
How's it going?
doing well. Looking forward to our topic here today.
Yeah, all that modal data we gathered before, assuming, once we think it's correct and good, we may want to calibrate a simulation model with it. Does that sound exciting?
That does sound exciting. It seems like it would be useful to know that your model is accurate. That seems like a helpful thing to know.
Yeah. So we're going to use some tools in this in order to, do this calibration process. And that's because well, one nice thing about Test Lab, our testing software, is part of this SimCenter family of products, which not only include testing, but they also include simulation. The tools are designed to work together, and we're going to try and show that for doing a correlation between simulation and test. All right. So let's think about this, the correlation of test and simulation, the philosophy. I don't know who wrote that slide. Must be a philosophical fellow, but we can do testing for simulation. So that means we'll validate simulation models, see if they're accurate and reflect reality. So that's using the real life tests. We can do simulation for test. And that's something I think we'll also be showing. Before we do our test, we could go out and do some virtual instrumentation so that we can kind of get some guidance on where we would like to measure during the test. And then we can sometimes even use test and simulation at the same time. So these are things like system in the loop, hardware in the loop, where a simulation model, like here they're testing a component on a test bench, but it needs to think it's hooked up maybe to a full vehicle or uh, a fuller test object. To fool that component into thinking it's part of a larger object, we could use a simulation model to, put the right drag on it and everything else. Kind of makes sense to you?
Yeah, okay. So it's like kind of like that left box we're using test to help the simulation folks out. The box on the far right, we're using simulation to help the test folks out. And then that middle one there is kind of using the two together at the exact same time.
That's right.
Okay.
Three modes. So let's start by talking about maybe a little more traditional thing. Bef- Way back before there was simulation, and I go way back. Uh, in order to build a product, a lot of prototypes were built. So you'd build hardware, and then you try and validate that that hardware is good. So you'd actually build what you intend to mass produce and test it out by putting it on a durability test rig or putting it in the field, see how long it lasts. You'd see how long it lasts, and then you'd come back and build a new design. So that was new hardware, validate it, keep checking if things are working properly, tweak it again, build hardware, validate, etc. So that took a while to come up with an actual uh, final design and release it, right? Because there was a lot of hardware prototypes that were built. Does that seem like it would take a bit of time there, Nick?
Yeah, I mean, building hardware isn't instantaneous. You have to wait for machine parts to come in, wait for stuff to get shipped together. It seems like it could take a real long time.
Yeah. And the promise of simulation was, hey, let's do a lot of those iterations or as many as possible on the computer. And we can modify things pretty easily there, test them out, and have that corrective feedback loop before we build hardware. And it could be that there's, in some cases, a few pieces of hardware built, but less than before. Or some companies want to even get to the point where they don't even build the hardware, they go right to production. So, or you might build one prototype and sign off on it. So the idea is to take a lot less time in the development of a product by using simulation. Kind of make sense so far?
Mm-hmm.
That's all great, but um, usually to get to that point, we have to have confidence in our simulation model. And how do we know it's good? Well, we might have to do some testing to see that the assumptions we make when building our computer model are valid. So you might model spot welds a certain way. You might decide to model a fluid in there a certain way. You have things with certain thickness, or you assume a certain material property, but you don't know if it's the right material property. So usually what's nice is because we're building products in successive generations, we can calibrate the model with our current product, right? Do you see this corrective feedback loop on the left here, Nick?
Yep.
And if we take the time before we make our next generation product to kind of validate all the assumptions we made in the building of that simulation model, we can have greater confidence over time that we're improving our modeling process. So the FE, finite element modeling process, is being continuously improved generation to generation of the products. And so you would have to test out less assumptions on the next generation of the product. And you'd learn all these modeling nuances each time. Kind of, well, does that make sense to you, Nick?
Yeah, so kind of our general goal is not to eliminate testing from the development of a product, but it's to be able to reduce the development cycle or the development time by using that test data to calibrate our simulation models and do as much of the design in the digital space as we possibly can. Is that
That's
right?
right. That is right. But to do it, we need to be checking those assumptions in the digital space. And I think the reason why we have this diagram here is your company has to give you the time after product one is released to check out your assumptions, to do your process improvement before you go on to design product two. And in some places, there's such a hurry, they don't bother to do that calibration or checkout after the first generation product. So very important that, management, et cetera, buys into this and wants you to be doing this calibration and checking of the assumptions. Any questions on that, Nick?
No, it seems clear, and it's even a nice little feedback loop there to show the kind of the loop between simulation and test, each kind of, helping the other perform better.
And it's not just time to market. The better your design, you can minimize failures in the field. You can reduce warranty costs. You want to achieve this design first time. So not just shortening the product design cycle, but making the products better would be another goal. Okay. So we talked about this before, but we'll review it again for those of just joining us. A good tool we can use in dynamic models where you have modes or natural frequencies of the structure is something called a modal assurance criterion. Modal assurance criterion, or MAC, tells you how similar two mode shapes are. I'm going to kind of draw on the slides here because I like to draw. We have two mode shapes here, and they have some vectors, right? Mm-hmm. Let's see if I can find my mouse. So a vector here and a vector over here. And we take the dot product of these vectors, and if these things are moving together the same direction, then the dot product is 1. If one of these dot products was orthogonal to the other, like this, so that one is orthogonal to the same point on the structure adjacent, then the dot product is 0. And in this case, if we were to look at all the points, are they all moving the same from the mode shape on the left versus the right, Nick?
I would say yes. They all appear to be moving in the same direction.
Yeah, then we would have a modal assurance criterion of 100%. Now, sometimes the points might be moving differently. And again, you have to kind of do this on an average basis. But if they're moving differently, if they're orthogonal, so to speak, not moving the same, What would the MAC be for these, would you guess?
I expect it to be very low, maybe a couple
Yeah,
percent.
yeah, much closer to zero, right?
Hmm.
So low. All right, that sounds good.
And that's a good
So,
MAC value, Pete, right, for 2 if we go back to that last slide. That's a good MAC value for, 2 different mode shapes. We might have mode 1 on the right and mode 2 on the left. And we expect our mode shapes to be special snowflakes. Each one is completely unique. So we expect that MAC value to be, in this case, very low.
yeah, for example, if this is 101 hertz natural frequency, this one is at 211 hertz natural frequency. Very different frequencies. You don't expect mode shapes to be the same.
Okay.
You should have a unique mode shape per frequency. And so sometimes problems arise, like we saw before the break, when we have two different modal frequencies. So these are at two different natural frequencies, but the shapes, what do you say? Do they look different or the same?
They look almost identical.
Yeah. And because they look identical, the MAC value is very high, yet they're at two different frequencies, so that's a bit unexpected. And we discovered before the break that that's because we weren't measuring at enough points. Like here, we have bending along the center. And because we didn't have any points along the center when we did these measurements, we didn't see that. So here we measured at 6 points. The mode shape is correct at those 6 points, but because we didn't take enough points, we're missing the full mode shape, right?
Yep.
And we interpret incorrectly how the structure is behaving. On the other hand, if we go over here, if we look along one of these lines here, same thing. We didn't measure along them in the 6 point, but with the 15 we did, and so we see that this mode shape in effect is unique. If we looked at just the 6 points we measured, even in this 15-point thing, we'd see that everything's kind of moving the same. So it's very important, I guess, if I'm going to execute my test, and I think we're going to do some simulation for test here, we want to know if we're going to measure enough points. How do you think we can go about doing that, Nick?
Well, Pete, I'm really not too sure. We need, I guess, some way of maybe trying to choose a subset of points, do a modal analysis, and then look at the MAC, and maybe we could add in more points if the MAC is not sufficient.
Yeah, that sounds pretty elaborate there, Nick, but I think I follow what you're saying. So let's maybe do an example case here where we got an exhaust system. And so when we have this exhaust system, the question would be, how do I'm going to do a correlation study. I want to make sure my finite element model is very accurate. I got all my elements. I can calculate shapes. And then the question is, if I was going to test for this shape, I'm not going to test at every single point here. It'd be prohibitively expensive. How many points would I need in order to describe this mode shape? What's your guess there, Nick?
So it looks like there's a decent amount of motion at each end of this exhaust. So you would need maybe 1 point at the left end at least, and 1 point at the right end. And then it looks like there's maybe an antinode or a maximum somewhere in the middle of that exhaust. So maybe 3 total points to describe this particular shape.
So 3 like this.
Yeah, I think that would work.
I buy that. But are we going to correlate just one mode?
No, we'd like to, I guess, correlate all of the modes within our frequency of interest.
Okay, well, if I was looking at these modes, how many points would I then need?
Okay, so that's a little more complicated. You probably still want at least 1 on the left end, and maybe 1 or 2 points in the middle. and then maybe a point at that, that Y junction that looks like it's wagging back and forth. You'd probably want a point each on each
Yeah.
pieces of that pipe.
Yeah, the mode shape on the left is the same one we had before. We decided we needed 3 minimum. But yeah, now we have a more complex mode shape, higher frequency on the right. We're going to need a few more points. So something like this, at least 4 or 5 points, I would wager, are needed in total to uniquely distinguish these modes. So how many modes does an exhaust normally have, Nick?
Probably more than 2. I can say that with confidence.
Yeah, it depends on the frequency we go up to, but if we're interested in sound of the exhaust, for example, how high in frequency can humans hear?
Well, I guess ideally up to 20 kilohertz, so although functionally, I'm not sure I can hear that high in frequency.
Yeah, but that's several modes. I'm only showing 6 here, and you can see it'd be pretty hard to determine what modes we need. So as you suggested, we got a tool, and just to kind of point things out, SimCenter Test Lab allows you to view and animate modes from simulation or test. It lets you do Mac, typically done on test. We're going to use a tool here for a second called SimCenter 3D that has some additional capabilities. I'm going to show you this pretest capability. It also lets me update models and do Mac contribution analysis and some other things that are not in Test Lab. And the idea of SimCenter 3D is I can do this pretest where I give it some initial points. I can tell it the off-diagonal Mac should be below a certain threshold, and it'll tell me how many points I need to measure in order to uniquely identify all the shapes. Kind of makes sense?
Yeah, I think so.
Let's see after I show it if it still makes sense. So I'm firing up SimCenter 3D here, and I believe I have the exhaust system simulation model available, so bear with me a second. And here it is, so I'll open it up. And we got our exhaust here, and I can select points on it, rotate it around, all that good kind of stuff. If you have it and you have tokens in SimCenter 3D, there is a correlation tab where you can create things like a pretest analysis. And when you create the pretest analysis, you can come in here and you can set some parameters for it. So I'm going to edit this. And you can see here, I can say, okay, I have uniaxial accelerometers or I have triaxes. Can I describe using 4 triaxial sensors, the motion in this exhaust across all the modes that I have identified?
Oh, okay. So that's kind of nice. It lets you, maybe based on the channel count and the number of sensors that you actually have in your test lab, it allows you to see if based on the equipment that you have available, whether or not you'd be able to kind of see all of the modes of interest in your structure.
Right, and I've identified 13 modes up to 137 hertz here.
Okay, and these have been calculated on the simulation model.
Yeah, these I've calculated on the simulation model. Part of the reason I mentioned it, I'd probably get a very different result if I calculated modes on my simulation model to 20,000 hertz. So I have to decide the frequency range and the types of modes I'm interested in. So I set that to 4. I'm going to run the model, so I'll hit solve here. And then after it's solved, I can come in and I can look at a MAC, and this is the MAC based on the 4 locations. You can see there's the ends there and some other stuff was selected. And if I look at this, I can see that some of these off diagonals, what were they ideally?
Ideally, they'd be 0 or very close to 0.
Yeah, like here's 11.01, so 1%. But yeah, some of these off diagonals are at 60% and they're orange. So that means the modes are 60% alike when I used 4 triaxial accelerometers. So let me come back over here and reset the calculation. So what I'll do is I'll come in here and I'll say, what do you want to do, Nick? Go up to 8, go to 6.
Yeah, why not 8?
All right, I think we can afford 8. If not, we can move our 4 cells twice. I'll solve it, and then I'll go here to correlate, and I'll grab the MAC with 8. Ooh, what do you think, Nick?
That's looking quite a bit better, Pete.
Yeah, looks like we're below 1%, 4%, very low on the off diagonals. That means we've nailed each mode shape very, very uniquely, right? And so we have enough points in order to identify all the modes uniquely on this, well, simulation model. If we use the same modes in the test, or the same points, the same nodes in the test to measure, we should be able to tell the modes apart because the mode shapes would be unique.
Okay.
Okay.
So here we've used our simulation model to help the test engineer avoid, I think, what we called in the last session, spatial aliasing.
Right. You know, under testing, I guess, not enough points. But we could over test too. Mm-hmm. So, I mean, if we measured at 100,000 locations, that would be very time consuming and not yield us more information than maybe those 8 locations. So yeah, here we can go in and it'll pick out some points. And it'll show us our off diagonal back. So initially we had some pretty high off diagonals. Along diagonal, it's normal that it's a full 1 because it's the same modes, just at a few points. Like in this case, it was something like 4 points. And then when we went to 8 points with additional nodes, then we got the off diagonals very low. So we had some good idea that we have enough points identified to do our measurement. Okay?
Okay.
All right. Then, if we're satisfied, what we would do is we would export these points directly off the FE model as a test wireframe. And then you could go and perform the test using the same geometry that you exported from the simulation and calculate your modes. And then when you're ready, you would, in SimCenter 3D still, bring in your test modes, bring in your simulation modes, and then how would you decide if you have a good simulation model or if it needed some updating or changes?
Well, I guess we want to, we could look at both the natural frequencies from test to simulation. We, hope maybe that they're similar. And I guess we could also look at the mode shapes at those natural frequencies and see how similar they are.
Yeah, I like this modal thing because MAC, modal assurance criterion, we get to use a lot and a lot. But this time, instead of doing a MAC with a set of modes to itself, we're doing it between the FEA and the test modes. So yeah, if we wanted to assess if the shapes are similar, we could do this analysis here, Nick.
Mm-hmm.
And what do you think of the results?
Well, they don't. I guess I'd say they don't look too bad.
Yeah, we would expect a strong diagonal, right, with high MAC values if the mode shapes are similar between test and FE.
Right, but I guess in this case we wouldn't necessarily expect for them to all be 1 like we would when we're comparing a set of modes against itself, right?
Yeah, but some of these go down to like 0.75. What do you think?
Yeah.
Is 0.75 good?
That might be okay. It looks like a couple of those higher in frequency fall off pretty high as well, even, worse than maybe a 0.75.
Yeah, like this one.
Yeah.
But yeah, and they're not in the same order.
Mm-hmm.
Some of the shapes, in one are at mode 13 in order of frequency, another one's at mode 11. So I guess we have what we call mode swapping. Yeah. If you were in school, was 75% a good grade?
it's a passing grade, Pete.
Yeah, so it's passable, but maybe we want really good correlation, and we could probably do better. So in this case, let's assume this isn't good enough. We'd love to see, especially for a simple metal structure, 90%, 95% or above along the diagonal, over the range of a few hundred hertz. So the next question is, how do we start to understand this? Now, you mentioned another idea that we could look at the difference in frequency. And in this case, it's a difference in frequency of what we call mode pairs, which we have written over there. So mode pairs, if I go back here, they're pairs of modes that have a higher Mach, like 50% and above, right?
Mm-hmm.
In this case, there's probably about 13 mode pairs or so, 13 modes that are somewhat similar. We think they're the same thing, and we could calculate the difference in frequency. So along the x-axis here, we have mode pairs. So we have one from FE, one from test, one from FE, one from test. And this is the difference in frequency. And what does this tell you, Nick?
So it looks like for several of those mode pairs, there's pretty good correlation, I would say. But there are a few modes, especially that one at the far right and maybe that one in the middle, where there's maybe a higher than acceptable frequency difference between those modes.
Right. And so maybe those will have low Machs because their frequency's different too. So it's a clue like where you might want to start on your model. Now, let me give you a hypothetical situation.
Mm-hmm.
We were testing a plate. Probably pretty easy to make an FEA model of a plate, would you say?
Yeah, I would say so.
And you could, after we did it, let's say we got just a great Mach, 99, or in the 90s or so, 80s, whatever, on the diagonal. But our mode pair frequency difference looked like this. Now, what would you say about this where it's way off?
Okay, so the mode shapes look okay, but the frequencies aren't very similar. So in that first session, we talked about natural frequencies and how for a single degree of freedom system, the natural frequency is equal to the square root of k over m. So I wonder if...
K being the stiffness,
Correct.
or Young's modulus.
Correct, yeah.
And the m being the mass or mass density, yeah.
So I wonder if in this case, maybe, one of those two parameters, either the stiffness of the plate or the mass of the plate, is incorrect.
Yeah. If we fat-fingered something like the Young's modulus, and we made it 100 times stiffer than it should, then maybe all the FE modes would be higher than the test modes, right?
Mm-hmm.
And it still would have a great Mach. The mode shapes would be the same, but the frequency difference would be off. And that's what we have here. If I come in and I change the materials, just one global change to Young's modulus for this plate, because it's a uniform material, I can improve drastically my frequency difference, because we purposely did that here.
Okay.
And the reason why I brought up this exercise is, if you look here, will one change of Young's modulus, or assuming the mass is correct, improve everything?
Well, it looks like they're not all off by the same amount. So I would say
Right.
probably not.
And not in the same direction. Sometimes FE is higher than test. Sometimes test is higher than FE. So if I was to improve the Young's modulus to reduce this difference, right, it would come down. But this one would probably get worse.
Right.
So the moral here is, even if I look at this, I can tell already a global change of material is not going to hack it.
Okay.
Right? We need to go and look locally for changes to make. And a great tool for doing that is something called the Mach contribution. So this chart shows for a given mode pair, so one mode pair, what the Mach is. It's like 85% here. And it says if I remove this point, exhaust 154 from the analysis, that the MAC will improve. And that's the best point to remove to improve the MAC for this mode pair. So 90%. And then it shows the other points in descending importance. What it's doing here, and it's going to help us find exactly where on the structure we need to change something, because exhaust 154, we can go and look there, is it's doing something like this. So let's say, and again, this is a hypothetical thing, we got 76% as our MAC for this mode pair between test and FE, whatever frequency they are. And it's at 76%. You can see the mode shapes are somewhat different.
Mm-hmm.
And what the MAC contribution does is it goes and says, well, if I could remove this point and recalculate the MAC, oh, look, it went up. So this point was dragging down the MAC by 2%.
Okay.
Now, we did these measurements. We don't want to throw this point out necessarily, but what we'll do next is let's look at and remove this point. Did that then improve the MAC? When we notice we put the original point that we removed back in. So we're going to evaluate each point by itself. So this point, the MAC went up by 1%, right?
Mm-hmm.
What did it go up by before?
2%.
2%. So we know that this point is only a 1% improvement. We could do the same thing here. Here's a 3% improvement. Here's a 4%. Here's that's a 13% improvement if we remove this one. And it kind of makes sense. These are moving pretty differently, right?
Right.
And so this is going to tell us, hey, look over here for where the discrepancies are between simulation and test. This is the area of the structure that's holding you down.
Okay. So
again, ultimately, we want to keep all the measured points, assuming they're good. Go ahead, Nick.
I was just going to say, so this correlation tool is kind of telling us where on the structure are our test mode shapes and our FE mode shapes differing. You know, at what location are we really seeing these large differences?
Yeah.
Okay.
And this is where the detective work actually begins. We know that we didn't have the greatest MAC. We want to improve it. Now it's giving us a clue where to look. And if I go and look at that Y pipe, I might see something like this. Hey, there's a weld here that I did not have in my original simulation model. Do you see this big weld?
Yep.
How a weld, why wouldn't it be, like if I used CAD geometry to create the FE model for my exhaust, why might there not be a weld in it?
Well, I guess maybe, it's something the modeler didn't initially consider how that part would be connected when they were building the model, or maybe, there was Friday afternoon and, they didn't want, welds can be a little difficult to model. Maybe they just wanted to hurry out of the office and go on vacation.
Yeah, another scenario too is in the CAD model itself, that you're not probably going to find the physical weld. What it'll say is put weld here, right? In the manufacturing process, the weld, then depending how they lay the weld and the size of it, etc., the weld shows up in manufacturing, but it's not in the CAD that you use to begin with. So this is the type of lesson that we would like to learn as simulation people. Like, okay, if in the drawings they call out putting welds in certain places, then I need to include the welds as physical elements in my model. Otherwise, I'm going to get the wrong results. So it pointed us to a certain place, but we had to go the extra mile and understand what was going on to learn the valuable lesson we need for the next time we make this model. And so by adding the weld, this is just by adding some weld elements at that end. This was before, this was after. What do you think, Nick? Did we improve this?
Yeah, I think it looks a lot better, especially for those last several mode pairs at the end.
Yeah, and that's pretty typical. You'll see probably overall improvement in general in that, the max frequency difference went from 15% to 6% off, and the lowest Mac went from 0.69. Now the lowest one is 0.8. So that we've improved things. And then now we can keep looking at the next mode pair and the next one, like maybe this one that's particularly low, and do the same thing, the Mac contribution, to go through and understand what's happening there to improve things again. So, what do you think, Nick, about this process of doing correlation?
Well, I'd say it seems pretty useful. It's hard to improve on a design if you don't understand, your current design in the first place. So this seems like a good way to make sure that your models are up to snuff and accurate, and that they can be used to, if you wanted to test out multiple variants of some product in simulation instead of in the real world, you better make sure that your model is accurate.
I agree with you. And I think the other thing to maybe point out, automatic updating is possible. Still there, Nick?
I am still there. I'm trying to decipher that word you've written on the screen.
That's the word updating.
You've got a doctor's handwriting.
I want to point out, like, at some point you could do automated updating if it's really small tweaks. And we do support things in Nastran like Solution 200. So they often write it this way, Sol 200, that's a 2, to do updating on models. If you want to learn more, you can come to the Siemens community. Have you ever used the Siemens community, Nick?
Yeah, I use it all the time.
Yeah, it's a pretty useful tool where there's a lot of useful articles. Let me maybe show it to you. I'm on Google here. I can say Siemens community. And it's the Siemens Digital Industry Software. That's why it says DISW. And again, the test products are part of the SimCenter family of products. So you're welcome to learn about NX, CAD, Teamcenter, everything else. This is free to the whole world. So you can come in here and you can go into like things like SimCenter testing, where it has articles, even a index of articles. And that index has things like sections on structural dynamics and things like that. There's tags and all sorts of good stuff. So let's say I wanted to learn about modal data acquisition and natural frequencies. I'll just pick something at random here. So this shows me something about natural frequencies and how they work, and has an in-depth explanation. I think we covered some of this in our first part of the session that we did, Nick. And then it also has things like, if I was to search around, like SimCenter 3D correlation, if I was interested in updating my models, I might find articles and things on the topic. So how to get test lab projects in SimCenter 3D, drivers, correlation, and modal, simulation with modal test results, things like that we can do. So lots of good articles about how to do things on the site, and fundamental knowledge articles about natural frequency, things like that. What do you use it for, Nick?
I like a lot of those articles, Pete. Things like the natural frequency and resonance. A lot of good articles on topics other than structural dynamics, acoustics, durability as well. So it's just a nice resource if you're looking to learn more about the SimCenter Test Lab software, or if you're looking to understand some background theory a little better.
Yeah. So what do you do, Nick? Like over the winter, there's nothing to do, so you curl up in front of the fireplace, get out your laptop, and peruse the articles. Is that kind of...
Yeah, that summer vacation on the beach, drinking a Mai Tai and learning
and
a little
reading
more
articles.
about yeah, exactly.
Well, Now there is a login over here, and that login, it's free to create, so there's no charge for that or anything. And what that lets you do is simply post questions. So you have to log in and create a little account in order to, there's forums, discussion areas where you can ask questions about anything you want, and experts around the world will weigh in and answer. So you can read everything without logging in, but if you wanted to ask a question yourself, then you just take a few minutes, create a login, and you can start posting and asking questions on the community, including things like the structural dynamics topic page, etc. All right, so I wanted to thank people for attending. If you have questions later on for Nick or myself, feel free to contact us. Our emails are here. You have any final thoughts you want to share, Nick?
No, I don't think so. Just appreciate everyone who attended, and hopefully we'll see you next time.
All right, I'm going to go to the beach and drink a Corona, as you suggested, and start reading articles. That sounds like a good way to gain some knowledge.
Sounds like a good way to relax.
All right. Thanks, Nick.